Section 18, Derivatives and Graphs with the Mean Value Theorem. The first big idea here, I have it split into like two big concepts. First one's I'm going to give you a derivative graph, and you need to glean information off the derivative graphs. So where's the thing decreasing, where's the thing increasing, where are inflection points, where might be the max of the function, where might be a minimum of the function. And then the second thing is you need to use the mean value theorem. The mean value theorem just guarantees that the slope of on a continuous interval between 2 points, the slope of the graph needs to match the average slope across that interval at some point. And we'll talk more about what that means. It makes way more sense with a graph. Okay, so down to our example problem. Let's just jump straight in. And we'll just talk about where everything I'd asked for exists on here. Alright, first of all, let's answer the questions. For which values is f of x decreasing? Well, this is a graph of the derivative. So where the derivative is negative, like here and here, our original graph is decreasing. So all I have to do is say between -2 and -1, and between 1 and 2. And that would be the answer to that question. If I ask where is it increasing, it'd be here. So from -3 to -2, or -infinity to -2. From -1 to 1, and from 2 to wherever you think this goes off to, infinity. If I asked you for maximums, maximums are increasing to decreasing, so it's wherever we switch from a positive value to a negative value. So that would be like here. This would be a max. This would also be a max. Our minimums would be where the graph switches from negative to positive, because decreasing to increasing is a minimum. It creates like a trough like that. So this is a minimum, and this would also be a minimum on the original graph, is the caveat with all that. All right, inflection points, that's where my derivative is equal to 0, because, okay, so inflection points generally happen when the second derivative is 0, but since this is already a graph of my derivative, the derivative of this graph will be the second derivative. So the slope of this graph, where the slope is 0, will be where my inflection points are. So my inflection points happen at about -1.5, about 4, and at about 1.5. That's it. Okay, now the last part says, for the graph at the left, ignore that it is technically a derivative graph. We're just going to apply the mean value theorem on this interval. So I'm going to erase all that max and min stuff so I can focus on making this. Alright, so from -2 to 1.5, that's my average slope is between those 2 points right there. So I can connect those up. And somewhere on the interval between these 2 points on this curve, my average slope needs to match my instantaneous slope. So I need to look for spots on the curve approximately where that would happen. So I see one right here. Like there. That spot looks like it has exactly the same slope as our average slope. And I believe I also see one up here. That one has about the same slope. And then I also see one like right before the slope of the point, like right on top of where the other one was, like right here. So I pointed out like 3 different spots where I thought the instantaneous slope equaled the average slope. So estimate where the mean value theorem is satisfied. Well, it'd be here. So at about negative 1.6 at about equals x. About x is equal to, oh well, not put the abouts, that just makes things confusing. All right, x is equal to negative 1.6, x is equal to, next value was around 0, and lastly at about 1.4. And those are the 3 points that I said the instantaneous slope equaled the average slope. So these are very different questions that are being asked in this section. One of them is the mean value theorem, which has you doing this, just figuring out the average slope approximately and then estimating it where it is. And then the other part is reading the graph to pull off the inflection points, increasing, decreasing, maxes, and mins.